From the phone in your pocket to the lights in your ceiling, our entire world is powered by electric circuits. Now, they can look pretty complicated, but the core ideas, they're actually way simpler than you think. We're going to break it all down, and we're going to start with a question that really gets to the magic of it all. I mean, really think about it. You flip a switch on the wall, and a light all the way across the room just, bam, it's on. Instantly. It feels like something is moving at an impossible speed. So what's actually happening in that split second?
Okay, so here's the big secret. It's not some little electron running a marathon from the switch to the bulb. The wires are already jam-packed with these charges, just waiting. When you flip the switch, you create an electric field that zips through the wire at nearly the speed of light. It's like a wave of command that tells all the charges to start moving at the exact same time.
All right, so to really get a handle on how circuits work, we need to meet the three main characters in this whole story. These are the fundamental building blocks of pretty much everything in electricity.
First up, we've got electric current, which we call I. This is simply the flow of charge, and we measure it in amperes, or amps for short. The absolute best way to picture this is to think of water flowing through a pipe. The current is just how much water is flowing past a certain point every second.
So what makes that water, our current, flow in the first place? Well, that's voltage. You can also call it potential difference. It's the push. It's the electrical pressure that gets those charges moving. If you don't have any voltage, those charges are just going to sit there. It's that simple. No push, no flow.
And finally, we have resistance, or R. It does exactly what it sounds like. It resists the flow of the current. Going back to our water pipe analogy, resistance is like a narrow spot, a little pinch in the pipe that makes it harder for the water to get through. Everything, a light bulb, your phone charger, you name it, has some resistance.
Okay, so we've met our three main players, voltage, current, and resistance. But here's the thing, they don't just act on their own. They are all tied together by one beautiful, incredibly simple rule that is the key to understanding almost any circuit. And this is it, Ohm's law. It just says that the voltage, the push, is equal to the current, the flow, multiplied by the resistance, the opposition. This little formula is your golden key. It unlocks how basically every simple circuit works. Let's look at it in action. Okay, don't let the table scare you. It's really straightforward. Imagine you have something with a constant resistance of, say, 10 ohms. See what happens? If you increase the voltage, the push, from 30 volts to 40 volts, the current, the flow, has to go up too, from 3 amps to 4 amps. The resistance, that V divided by I, stays locked at 10. More push means more flow. It's a perfect relationship.
All right, we've got the rules of the game down. Now for the fun part. Let's actually put this stuff into practice and see how we can wire things together to build circuits. So there are really two basic ways to connect things. First, you've got a series circuit. Think of it like a one-lane road. The components are all lined up one after another, so the current has only one single path it can take. But then you have a parallel circuit. This is more like a highway with multiple lanes. The circuit splits and the current can take different paths. And trust me, that difference changes everything.
Okay, time for a little pop quiz. Let's say I hand you 5 little resistors. Each one has a tiny resistance, just 1/5 of an ohm. How would you hook them up to get the absolute biggest, the maximum possible resistance you can?
You guessed it, you connect them in series. You put them on that one-lane road. When they're in series, the current has to push through every single one of them. So to find the total resistance, you just add them all up. 1/5 plus 1/5, 5 times, gives you a grand total of 1 ohm.
So what if you wanted the exact opposite, the minimum resistance? You'd connect them in parallel. By opening up all those extra lanes for the current to flow through, you make its journey way, way easier, and the total resistance just plummets, all the way down to a tiny 1/25th of an ohm.
Now, these rules seem pretty simple, right? But believe it or not, there are a couple of really common myths that trip up almost everyone at first, even university students. So let's bust those myths right now.
Okay, this is a big one. It's so tempting to think that a battery is like a pump that pushes out the same amount of current all the time, no matter what. But that is absolutely not how it works.
Here's the truth. A battery provides a nearly constant voltage. It provides a constant push. The amount of current that actually flows depends entirely on what you connect to it. It all goes back to Ohm's law. If you give it an easy path with low resistance, a ton of current will flow. If you connect something with high resistance, very little current will flow. The push stays the same, but the flow totally changes.
All right, here's another one that just feels intuitive. You see a light bulb glowing, so it feels like the current,
The electricity is getting used up or turned into light. It makes sense, but it's wrong.
The fact is, charge is always conserved. It's a fundamental rule of physics. It's not created or destroyed in a circuit, so the current isn't used up. Think of it like a bicycle chain. The chain moves and makes the wheels turn, but the chain itself doesn't disappear. For every bit of charge that goes into a light bulb, the exact same amount has to come out the other side.
And we can prove it. Look at these diagrams. We have a simple circuit with a device called an ammeter that measures current. We've moved the ammeter to 3 different spots in the loop. But look at the reading. It's exactly the same every time. That proves it. The current, the flow, is the same at every single point of the circuit. So, what's the big takeaway from all this? It's that you have to stop thinking about a circuit as a sequence of events. It's not a domino effect. A circuit is one single, interconnected system. When you make a change anywhere, like flipping a switch, you're not starting a race. You're instantly changing the state of the entire system at once. It's a total shift in perspective. So we've covered the basics: voltage, current, resistance, series, parallel. The rules themselves are pretty simple, but as you can see, once you start combining them, the possibilities for what you can build are just endless.
So now that you know the rules, and more importantly, you know the common mistakes to avoid, I'm going to leave you with a little challenge. Take a good look at this circuit. You now have all the tools you need to figure it out. So, what do you think is happening here?